give everyone one more minute. No, no, no.
That's sort of like the sigmoid function
Yeah.
when people come in. So you'll still have the last few filing in at like 10:30.
Yeah.
So when I was an undergrad and there was a project due or homework due, people wouldn't show up to lecture if it was webcast.
Yeah.
Well, someone just asked on Piazza, why is the live stream link not working? So that's what I'm thinking. I thought maybe I can make an announcement to explain what's wrong with the live stream link, but that's kind of useless because everybody who here is already in the room.
So I was in Berkeley last night seeing the movie Ghost in the Shell.
By the way, just because the live stream is not working doesn't mean you're not being recorded.
Okay. Yeah, so this movie is it's a very highly acclaimed manga. So it's a Japanese animation, and it's on the, so it takes place in this futuristic world where humans have had various parts of them replaced by machines. So basically everyone is a cyborg to some extent, and people have had parts of their brains and bodies replaced. And the plot revolves around this this one rogue AI called the Puppet Master, who has developed its will of its own, and now claims to be a life form with its own consciousness. And so the movie is sort of exploring the question of can consciousness emerge spontaneously? And I was realizing that it's actually pretty fitting for this lecture, because the previous classes have been about imitation learning and have been about using optimal control to train policies. But the next lectures will not take that intermediate step of first using an expert to train a policy. So the theme of the next lectures will be, can optimal policies, or can good policies emerge spontaneously? So here's an overview of what's coming up. So today we're going to talk about Markov decision processes. This is some of the core mathematical formalism for reinforcement learning. And we're going to talk about the algorithms for exactly solving these MDPs, value iteration and policy iteration. Then we're going to talk about policy gradient methods, then Q-learning methods, methods for learning Q functions, and then some more advanced methods for learning Q functions. Then we're going to go back to the world of, then Chelsea's going to take the next few lectures and talk about learning models and imitation learning. And then I'm going to do a few more lectures about more advanced policy gradient methods and the exploration problem. So this lecture is actually going to make a stronger assumption than the subsequent ones. So in this lecture, we're going to assume that you have a known system with a finite number of states and actions. And we're going to use that to solve it analytically. And we're going to talk about some methods for exactly solving for the optimal policy. Value iteration and policy iteration, which you've probably heard of if you've taken an introductory class, and modified policy iteration, which is a little less well known, but we'll talk about that at the end. So we're talking about methods that are a bit less general, at least in practice, than some of the other techniques we'll be discussing in the course, because they assume you have this known model and everything. So why is that still useful for the other algorithms, which we're going to get to later? Well, the first algorithm we're going to talk about, value iteration, it turns out that if you modify that algorithm to take small updates instead of large updates, and to use a function approximator such as a neural network, you get these deep Q network methods, which we're going to talk about later. So those are sort of a straightforward way of modifying value iteration to work in the function approximation setting. Similarly, if you take policy iteration and you do small updates on the policy instead of big updates, and you use function approximation, you get the deep policy gradient methods, which we'll also be talking about in several lectures. So these methods we're going to talk about today are sort of they're the foundations for these more sophisticated methods that we'll talk about later. And in fact, Some of the ways we'll analyze the more sophisticated methods are based on the ways that we analyze these two simple algorithms. Okay, so first, let's just quickly review the definitions of Markov decision processes. So you have a state space, which is a set of states that the environment can be in. An action space, that's just a set of actions that the agent selects from each time step. And you have a transition probability distribution, which tells you the probability of the reward and the next state. So there are lots of different ways of defining it. I like this way because it's convenient in the largest set of cases, where we say that the reward and the state are stochastic as a function of the state and the action. But you can also just say that you have a transition model for the states, P of S prime given S and A, and then you have a deterministic, the reward is just a deterministic function of either the state action pair, or state action state prime. And these formulations are all equivalent in expressive power, meaning that if you have an MDP that is in one of these formulations, you can easily describe it using an MDP in the other formulation, and it doesn't make the problems any harder or easier. Okay, so there's also another kind of mathematical object, which is, well, a little more general. We can trivially map an MDP onto a POMDP. So we can say an MDP is a kind of POMDP where the observation is not stochastic and y is equal to s all the time. As it turns out, we can also say that a POMDP is a kind of MDP. And that's a little less obvious, but the way that works is you just define an MDP where the state space consists of the set of observation histories in the POMDP. So the state you receive at the first, or the state the agent is in at the first time step, is just the first observation it sees. So that's all the information it has at the first time step. Then at the second time step, at S, we define the state as the first two observations, and so on. So the state is just, it's a kind of information state of the agent. And so that way, this turns it into an MDP. Well, the MDP is going to be a lot bigger, obviously. And instead of having a nice, well, our state space of this new MDP that we just defined is going to be much larger than the state space of the POMDP. But actually, this isn't just an impractical mathematical construction. If you look at some of the methods for using function approximation, like if you're using recurrent neural networks, they actually effectively do this, meaning that they take all the previous observations, they take all the history, and they use those, they compute the next action or the next value as a function of that history. So, and in particular for recurrent neural networks, you compress the history into a vector. I won't, if you didn't get that, don't worry about it. You'll hopefully see it later. Okay, so just as a very simple example, which is going to appear in your homework, there's this is a toy MDP called Frozen Lake, which I actually made for last year's homework assignment, but it's now also in OpenAI Gym. So it's going to be in your homework assignment. The way it's just defined as, it's a grid world, meaning that you have an agent that lives on a 2D grid, and there's a start location where the agent always starts out, and a goal location where it's supposed to navigate to. And it's called Frozen Lake because the story is that there's a lake that's frozen over, and you threw a frisbee and it got stuck out in the middle of the lake, so you have to go retrieve it. But the ice is really slippery, and there's some holes where the ice has melted. So if you step in one of the holes, you're going to freeze. And since the ice is slippery, you don't always go where you want to. You don't always go in the direction you expect. So if you try to go forward, there's a 0.25 probability you'll go left and a 0.25 probability you'll go right. So that makes it pretty hard to navigate to the goal location in this stochastic environment. Okay, the episode terminates where when you get to the goal or the hole location, and you receive a reward of 1 if you successfully reach the goal. And so that's how the MDP is set up. I'm just mentioning it now just so you can have a picture in your mind when you think about these algorithms for solving MDPs. When you have a finite MDP like this, then everything is just an array of some sort. So the transition distribution is just an array that tells you what's the probability for each next state that you could reach. And assuming you have a deterministic reward function, it's just going to be either a vector or a matrix telling you that, how much reward you get at each state or state action pair, and so on. Okay, one last definition I'll provide before getting into the more meaty subjects is policies. So a policy is just how an action is how the actions are chosen. So there are 2 kinds of policies that we'll be using: deterministic policies, where the action is just a function of the state, and stochastic policies, where it's a conditional distribution given the state. Okay, so why do we bother to define this concept of an MDP as opposed to just defining the optimization problem we want to solve? So the reason is that there are actually a lot of different kinds of problems we might want to ask about a lot of questions we might want to ask about an MDP, as opposed to just maximizing one particular kind of objective. So the main kind of problem we want to solve is policy optimization. So here you're trying to maximize the expected reward, which is a function of the policy. So you have a policy which is deterministic or stochastic, and you have a stochastic environment, and you're trying to maximize this sum of rewards. And this infinite sum only makes sense if the MDP is such that is designed in a way that this is guaranteed to be finite. But there are other ways that this sum can be guaranteed to be finite, which we'll discuss soon. So the other question we can ask about an MDP is what's the expected return for a given policy? So this is called the policy evaluation problem. It's usually actually a subproblem of the policy optimization problem, but it's still worth making a distinction between them. So in policy optimization, so the return is just is the sum of the future rewards in an episode, starting from a given state. This is a term we'll be using a lot. It's a random variable, and the 2 main versions of this that we'll be interested in are discounted return, where you take, so let's say we're considering the return starting at time step t. In the discounted return, we multiply by this discount factor, gamma, which downweights the terms in the future. And so we'll be considering this discounted return and the undiscounted return where we have a trajectory of finite length, capital T in this case, and we just care about the sum of rewards up till capital T. So that's the return. And the quantities we'll be interested in evaluating are, first, what's the performance of the policy? These 3 quantities are just in the discounted, just written down for the discounted setting. So we're interested in the return of the policy, which is just a single scalar. We're interested in the state value function, which, given a state, tells you what's the expected return if you start at that state. And we'll be interested in the state action value function, especially in the later classes. So that's telling you what's the expected sum of rewards if you start out in state S and then you perform action A. And this is going to be interesting because it lets you measure which actions are better than the others. So if you know what the state action value function is, you know which actions are good. Okay, so now we're going to start getting into value iteration. So value iteration is actually pretty closely related to dynamic programming algorithms, which you might have seen in other computer science courses, like an algorithm course. And it's actually quite useful to take on that perspective of value iteration as dynamic programming. So let's just look at the finite horizon setting. So here we have a finite we have a finite number of time steps. We have capital T is the number of time steps, and we're trying to maximize the sum of rewards. And then there's a value there's some function v at the last time step that you receive, which is just tells you the reward for being at a given terminal state, or being at a given state at the last time step. So we're trying. This is what we're trying to maximize, in this finite horizon setting, there's no guarantee that the best possible policy is going to be stationary, meaning time independent. So the optimal policy for this setting might be time dependent. That's why we have to write pi 0, pi 1, and so on up to pi sub t minus 1. So we want to maximize the expected sum of rewards with respect to all of these policies at different time steps. By the way, this is exactly the same thing as LQR, which you learned about 3 classes ago. But I'm going to go through the derivation again with the new notation, so you're familiar with this notation. But LQR is exactly value iteration, by the way. So okay, so to do this, to solve this maximization, we can just move around our expectations and our maxes. So you might notice that R0, R1, and so on don't depend at all on pi sub t minus 1. So we can move that through all of the R's all the way till the end. And we can keep doing that until we end up with an expression that looks like this, nested like this. And now that we have this, now we can do something, because this inner expression doesn't involve a search over an exponential number of possibilities, like all the possible policies. This is just a search over one policy. So what we can do is just evaluate this inner term. Let's say that what we obtain we obtain pi sub t minus 1 and v sub t minus 1. So that means that pi sub t minus 1 is the argmax for each state of this expectation, and v sub t minus 1 is just the max. So when I say maximize, I mean that it's returning the argmax and the max. So then we look at our original expression again, which is this, and we say, okay, this last term right here, this last max, we can just replace by the value function that we just computed. Or we can replace it by v sub t minus 1. So now we just got rid of that term, and we replace it by v sub t minus 1. And now this expression looks exactly the same as the one we had up here, except there's one fewer term. So we can keep repeating that process until we've solved for all the policy and the value function at all time steps. Where the value function tells you the expected sum of returns or sum of rewards after that time step. So this is how the recursion works. And just to write it out more precisely, we just go backwards in time, and each time step we solve this little maximization problem to solve for the policy and the value function. And that's like the same thing you did in LQR, except there you had a quadratic function for the value function, and you had a linear policy. And that turned out to be correct in the case where you have a linear dynamics and quadratic cost. Okay, so now we'd like to move on to problems that have an infinite time horizon, because these methods with finite time horizon well, first of all, you might have a really long time horizon, so you don't want to have to solve for it doesn't make sense to solve for a different policy and a different value function at every time step when you have a million time steps, and most of them are almost the same. So it makes sense to move into a setting where you can deal with an infinite number of time steps. And to do that and make everything finite, and to make this possible, we need to introduce a discount factor to make all of our sums add up to finite numbers. So the discount factor is just a number between 0 and 1, and we're going to use that to compute a different kind of return called the discounted return, where we weight the rewards by this factor. So we downweight rewards that occur far in the future. So if you look at this this exponentially weighted sum of rewards, or this geometric you can say it's like a geometric series of weights. So we have this, our sequence is 1, gamma, gamma squared, and so on. And if you add up all these coefficients, it's 1 over 1 minus gamma. So it's like we effectively have 1 over 1 minus gamma time steps. And you can think of this as an effective horizon. So if you optimize the discounted return, it's like you're optimizing a finite horizon return, except with 1 over 1 minus gamma time steps. So we want to solve for, what we want to do in the discounted setting is we want to find a policy pi that optimizes the discounted sum of rewards from each state. So instead of trying to maximize the sum of rewards for all time steps in the future, we care about the time steps in the near future more than the far future. So this actually, just as a side note, this discounted problem, we can actually, it's equivalent to a problem that we can set up with a undiscounted MDP, where we say that there's this sink state, and when you get into this sink state, you get 0 reward and you're stuck there forever. So we introduce this sink state, and we say that there's a transition to the sink state with probability 1 minus gamma. And if you set this problem up, it turns the undiscounted MDP into a discounted MDP. And this is like, so you can think of, the way you can think of discount factors is, like I can eat the marshmallow today, or I can eat it tomorrow. So which one is better? Well, I might get struck by lightning between today and tomorrow, so it's better to eat it today because there's a probability of 1 minus gamma that I'll get struck by lightning. So that's sort of a justification for using discount factors, which goes along with this sink state idea. Okay, so now we want to derive an algorithm that's going to solve for the optimal policy and the optimal value function the way we did in the finite horizon setting. But so how do we can't do the exact same kind of derivation because our derivation required looking at the last time step and working our way backwards. But now we have nowhere to work backwards from because there's an infinite number of time steps. So how do we do that? Well, okay, let's write the returns expression we're trying to optimize in this form with the nested sum again. So what we're going to do is let's just pretend that there's a finite horizon. So let's just ignore all rewards starting at time step capital T. We can solve this finite horizon problem using value iteration, which we just learned about, or using the finite horizon version of value iteration. And then the question is the solution to this finite horizon problem, is it close to the solution for the infinite horizon problem? And the answer is yes, because if the rewards are bounded, let's say they're bounded by R max, then there's a finite number that these future rewards that you're ignoring can add up to. So in this case, you're ignoring a bunch of terms in this geometric series, and the total that you're ignoring is less than or equal to R max times gamma to the T over 1 minus gamma. So since we're just ignoring part of the sum, our solution can be be worse than the true solution by at most that sum. So if we solve for a policy in this finite horizon problem and we compute the value function of that policy, the error in our approximation is going to be less than or equal to this sum. I mean this quantity right here. That's just because, in fact, it's going to be a well, I was going to, okay, let's not make assumptions about whether the rewards are positive or negative because we don't need to do that here. It's suffices to say that the error is going to be bounded by this because that's the size of the terms that you're going to ignore. Also note that when we do this process when we turn it into a finite horizon problem, we get a non-stationary policy because when you have a finite horizon problem, the optimal policy is going to be non-stationary. This argument shows that if you look at pi 0 and v 0, and you look at them as capital T goes to infinity, they converge to the optimal value function and an optimal policy. This argument wasn't very precise, but you can make this more precise if you want pretty easily. Okay, so if we just look at what's happening computationally when you do this finite horizon value iteration, it actually looks, well, we get this backwards. We can write it like this. So what you do is so we have n iterations, and this is going to be like the time we're going backwards in time. We're doing backups in time, but now we're just, instead of using a time index, we're calling it an iteration index n. So we're going to go, so each iteration, we look at all states and we maximize, we find the best action according to the next value function. So this is exactly the dynamic programming update, but just using n instead of t. So what you get at iteration n is just what you would get for v0 if you had a finite horizon problem with n time steps. So this is what the algorithm looks like, and using the arguments from the previous slide, this converges to the optimal value function and a optimal policy. Okay, there's another view that's also pretty useful, another view of value iteration and another way of proving convergence. So we can think of the value function as a vector. So here, S, remember S is the state space, the absolute value. Here, that notation, the bars mean cardinality of S, so the number of states. So V is just a vector of length cardinality of S. So the value iteration update is just a function that takes a value function and it spits out a new value function. This is called a backup operator because it propagates information backwards in time. So let's say you have the value function at time 10 and you do value iteration in the finite horizon setting. Now you have the value function at time step 9. But this also is meaningful in the case where you have an infinite horizon problem because it's looking at what's going to happen in the future and it's using that to update the value function in the past. So it's doing a bit of a look ahead. That's how you can think of value iteration. And this notation here, which you'll be seeing a bit, is this just means TV just means the backed up value function, and we're evaluating it at state S. So then, using this notation, we can write down value iteration, infinite horizon value iteration, much more simply. It's just you apply t a bunch of times until convergence, until termination condition. I won't talk about the termination conditions, except maybe if we have extra time. Okay, so using this, this perspective of value iteration as applying an operator, there's another set of analysis tools you can consider. So here, it turns out that the backup operator is a contraction. And what that means is if you have two value functions and you apply the backup operator to both of them, they become closer together according to some distance metric. And in this case, the distance metric for which it holds is the infinity norm, which just means the max of a vector. So if you have two value functions, you apply the backup operator, the max of their difference becomes smaller. That's pretty straightforward to show, and you can even think about it intuitively in terms of this finite horizon picture, where the maximum, I won't go into the detail there. So by this, okay, so there's a theorem called the contraction mapping principle, or the Banach fixed point theorem, which says that if you have a contraction mapping, it has a fixed point, which we're going to call V star here, and the iterates converge to this fixed point. Okay, so now, so that's it for value iteration. Are there any questions before I move on to policy iteration? Mm-hmm.
Yeah, just for clarification. So you start with optimizing a separate policy for each time step, right?
Uh-huh.
And then by running the series to infinity, then the policy for the first time step becomes the global optimal policy. Is that right?
Yeah. Mm-hmm. If it converges to, well, the value function will converge to being the value function of the optimal policy. And as a result, since that value function is the value function of the policy you have in this finite horizon problem, that also implies that the policy you get is an optimal policy. Right. So it's easier to reason about how the value function will converge in this case. So if you make the time horizon arbitrarily long, then your approximation error will become arbitrarily small because you're just ignoring some really tiny rewards that have been attenuated by the discount factor. Does that make sense? And then once you see that the value function is approximately equal to the true optimal value function, then it follows that the policy that you get for the policy pi 0 that you get is also converges to the optimal policy, or that becomes the suboptimality of that also shrinks exponentially. And since there's a finite number of policies, it follows that eventually it'll become an optimal policy. Any other questions?
Do you have to first run the value so running many times until it's becomes contract, and then we can do the evaluation of policy?
I didn't understand. So, yeah, sorry, could you rephrase?
We have to run it many times until it converges, and after that, we can then proceed to the next step, computational-wise.
For value iteration?
Yeah.
Yeah, so you need to run it, you need to keep doing these iterations until some stopping criteria is met. And then at that point you have a policy, well, with some stopping criteria you can guarantee that your policy is optimal. For others you might just want to guarantee that it's optimal to within epsilon. Okay, so now we're going to move on to policy evaluation. We're going to move on to policy iteration, but first we're going to talk about a subproblem of policy iteration, which is called policy evaluation. So the problem in policy evaluation is how to evaluate a fixed policy pi. So how to compute the expected return of this fixed policy pi. And this is actually a simpler problem than the one we just solved, because the one we just solved, we have to compute the optimal policy and we have to compute the returns of the optimal policy, whereas here we just have to compute the returns. So in this case, so we can actually go through the same line of reasoning to figure out how to do policy evaluation. We can consider a finite horizon problem where so now we have t time steps again. We can rewrite it in this as a nested sum. And when we look at the procedure you go through when you're to do dynamic programming to evaluate this nested sum, it again looks like it can be written as repeated application of this backup operator. Except now we have a new backup operator, which is called t pi, whereas our old one was just called t. And the only difference is instead of having a max over a on the outside, as we did for t, now we just have a is defined to be pi of s. So a is the action that our policy pi would have taken. So that's the backup operation we want to perform. And it follows from the same line of reasoning that this is also a contraction. So you can apply this operator by, you can apply it by an iterative method where you just, you can solve for this value function v pi by just repeatedly applying the backup operator. However, that's not the only way we can solve for it. It turns out that if you look at this, if you look at the fixed point equation, which is that v equals t pi applied to v, the fixed point equation is linear in v. So if you just write out the equation, we've got probabilities, and then we've got the reward function. These are all just constants. And then we've got v over here. And it's just, so this expression is this is an affine function of v. So we can just solve this, we can solve this equation. And that's actually usually the most efficient way to go about it.
This only really holds for like deterministic policies, right?
Right. So that's this equation only. This is only true for deterministic policies, and this only is correct for deterministic policies. But we could just rewrite this to say that A is sampled according to pi of A given S, and then this one we can we can also compute what the transition probability distribution is for a fixed policy pi. So then we get P of S prime given S, where actions are taken from pi, and the math comes out the same. So this same math works for stochastic policies, but I've just written it this way for simplicity. Yeah. Any other questions? Okay, so just as an overview, next I'm going to just go through, show the policy iteration algorithm. But as an overview, the way it works is first you start off by you initialize your policy somehow. You evaluate it to get v pi, the value function of that policy, and then you compute a new policy, which is defined to be the greedy policy of the value function you just computed. And what it means by what the greedy policy means is you look ahead one time step and you take the action that looks good if you just look ahead that one time step. So by looking ahead one time step, that means you look at the next reward and then you look at the value function at the next state. So that's the expression you're trying to maximize at each state. This should say, this is like how we're updating the policy. So this is what the new policy is going to be. So the nice thing about policy iteration is it's guaranteed to converge to the optimal policy and the optimal and the value function of that policy in a finite number of iterations for gamma less than 1. That contrasts with value iteration, where actually it also does converge to the optimal. It converges to the optimal policy, and it also does. It converges to the optimal value function, but you never actually get to the optimal value function. So actually, this is a slight mistake, or I misspoke a little bit. It should say guaranteed to equal the optimal policy and value function after a finite number of time steps. Whereas for value iteration, it converges to the right thing, but it's going to converge. Like the error will get smaller. Will get exponentially smaller, but it's never going to get exactly there for the value function. But the policy will eventually become an optimal policy. So that's the nice thing. So if you actually want to exactly solve an MDP that I give you, your best bet is to use policy iteration because, well, at least your best bet is to solve for the optimal value function exactly, as opposed to just waiting for value iteration to keep running. And actually, the value function in policy iteration, the value function converges faster in a precise way than. So the value function converges in policy iteration faster than it does in value iteration. So if you start off, I won't go into the details, but you can see it in this textbook by Puderman, which is a really good textbook that goes into the mathematical details of this. But basically, if you start off with your value function at 0 and your rewards are all positive, then the iterates you get from value iteration are always less than or equal to the ones you get from policy iteration.
When you say the value function converges, you mean the return of the value function converges?
So here I mean that yeah, that's a good question, actually. So the question was, what does that mean that the value function converges? Does this mean like the return of the policy, or does it mean the approximate value function you're computing? So actually, there are two things worth there's a distinction worth noting here. So in value iteration, you get a sequence of value functions, of approximate value functions, but these are never actually the value functions of any policy. These are just estimates of your value function. Whereas in policy iteration, the value function you get at each iteration is exactly the value function of the policy you have at that iteration. So you're getting real value functions in the policy iteration case, but not in the value iteration case. So when I said that the value function converges, I just mean that your approximate value function converges to the right thing. but it's never actually the value function of your policy in the case of value iteration. Does that make sense?
Yeah, I was just asking, so the value function means cost, right?
So yeah, it's the expected return conditioned on the first state.
Because it sounds like because in your example with the ice
Yeah.
field, it sounds like you're actually changing how much cost you get for dropping into the hole. But that's, I mean, the value function itself is set, right? It's just a return, so the cost that we get from running the policy.
Yeah, I mean, yeah, I can go into the details of that example more a little later if you're interested. Yeah. Okay, so we can write down. So now let's just describe it more precisely in this operator form that we were using before. So we initialize our policy pi, and then for iteration n equals 1, 2, 3, and so on, so we first update our value function by solving this linear equation, which you can solve to double precision. And then we update the policy to be the greedy policy for that value function we just computed, meaning that we do the one-step look ahead. We compute the expected one-step estimate of the returns. Does this make sense? Okay, and I won't go into the convergence proof in detail, but I'll give you a little sketch of why it works. So the main result is that the sequence of policies you get when you run policy iteration is monotonically improving. So that means that if you take your so eta here just means the expected return of the policy under some initial state distribution. So if you sample the initial state from some distribution, eta just indicates the expected return of the policy. So if you run this algorithm, the claim is that the performances of all these policies is monotonically increasing, and then since you have and then if it ever stops increasing, then you're done. So if you do an iteration of policy iteration and your expected cost doesn't improve, then it's guaranteed to be done, and you have the optimal policy and the value function of the optimal policy. So the rough argument for why this is true is, so let's look at, so the argument we're going to make is that if you just switch the policy at the first time step, that's going to improve the expected returns. Then we're going to say that if you also switch the policy at the second time step, that also improves the expected returns, and so on. So if we switch all of them, it'll improve the expected returns even more. So the way this works is let's look at the expected return. Let's look at the expected return before we make any changes to the policy. So pi 0 is our old policy. That's pi superscript 0, and pi 1 is the new policy. So before we have, this is a perfectly valid expression for our expected return of the policy. We look at the first reward, R0, plus the value function at the first time step. So now let's say we switch to the policy pi 1. Well, the way we define pi 1 is as the greedy policy of v pi. So that means that pi 1 chooses the action A0 that maximizes this expectation. So all we did going from this to this is we switched from any old action, or we switched from the action that pi would have taken to the better action that we take by maximizing. So that way, we just made the returns better by switching the policy at time step 0. So we can write eta of pi 1, pi 0, pi 0, pi 0. That means that we're switching the policy at time 0, and we're using the old policy at subsequent time steps. So then we can do the same trick to say that we improve things by switching the policy at time step t equals 1 and t equals 2 and so on. And eventually we get that eta of pi 1 repeated all the time is better than eta of pi 0 repeated all the time. So that means, okay, that shows us that the performance is monotonically improving. Then you can also show that if it doesn't improve, that means that you're at a fixed point of the Bellman equation. So that means that when you take the max over A of this expression, R plus gamma times V, that you get V back. You get the same thing back. And that means you're at a fixed point of the value iteration backup T. And that means you must have the optimal value function. So it implies that, so I just said that if policy iteration doesn't improve, if eta doesn't improve, if you have equality instead of an inequality, a strict inequality there, that means you're totally done and you have the optimal value function. And as a result, since the value function here is guaranteed to be the value function of your policy, you also have the optimal policy. So that's the rough argument. Does that actually make sense to people? Yeah.
So why is it not possible for like V to change a little bit in one time step, so that pi n and pi n plus 1 don't change, but it's sort of like on the way where a later pi n plus something will sort of change one decision and be better?
I don't know how to give a good explanation, but we can talk afterwards. Yeah.
So, the policy iteration thing will converge faster, but that's if you have discrete, discrete world, right?
That's right. Yeah. So, yeah, the claim that it converges faster has some caveats about, like, first of all, you have it only is true if you initialize the value function in a certain way for value iteration. Because let's say you initialize the value function to the optimal value function, then it's obviously value iteration will converge instantly. Whereas policy iteration, you start off with a policy, so it's not going to use a value. So it can't start off with that. Okay, so that's policy iteration. And here's something that's a little less well known than value iteration and policy iteration, but I think it's actually a pretty useful concept to be aware of. So informally, what we're going to do, if you look at policy iteration and value iteration so value iteration just does a one-step look ahead to update the value function, whereas policy iteration actually looks ahead an infinite. It looks ahead all the way. It looks at the whole infinite horizon return. And the advantage is you can get faster convergence, but the disadvantage is it might be computationally expensive to solve this linear system of equations. So for value iteration, you're just applying some affine, or you're just, well, to do a backup, it's basically just an affine operator and a max. So that's generally going to be cheaper than solving a linear equation. And so it's more efficient to, that's one reason why we're going to do modified policy iteration, because we don't want to solve that linear equation. But actually the more important reason is because this is actually a pretty good description of what's happening in some of the algorithms we're going to discuss later with neural networks. So in modified policy iteration, all it means is you don't update your value function to be the exact value function of the policy. You just do a finite number of backups using the backup operator tpi. So you update. You've got your value function. You set pi to be the greedy policy, and then you update the value function by doing k backups with the policy you just computed. So if you set k equals to 1, you get value iteration. And if you set k equal to infinity, you get policy iteration. So by this perspective, it's kind of clear why policy iteration is usually faster, because it's just doing basically the same thing, but it's doing more updates on the value function each time. And you can find more details in Peterman's textbook. It's actually hard to analyze modified policy iteration, though. So for value iteration and for policy iteration, there's a kind of, it's a pretty slick and short proof of why they work. Whereas for modified policy iteration, neither of those techniques work. And you have to, it's a bit more involved to actually prove that it converges. at least in the most general setting, it's a bit more involved. Okay, so that's all for the slides today. So the homework is going to be released later today, and it's going to ask you to implement these algorithms and apply them to some small grid world type problems. And it'll be due in 2 weeks. And next time we're going to talk about policy gradient methods. And policy gradient methods can actually be thought of as an infinitesimal version of policy iteration. So in policy iteration, you do this greedy step, this greedy update on the policy where you take the max over actions and you fully update your policy to be this new greedy policy. But that's not going to work so well when we do function approximation because it's going to cause too big of a change, and your value function is going to be way off. So what we do instead is we make a small update to the policy, but to make a small update to a policy, if you have a discrete action space, you can't just infinitesimally change a discrete action. The only sensible thing is to change the probabilities of the different actions. So for policy gradients, we're going to use stochastic policies, and we're going to change the probability each iteration. Any final questions? Nope. All right. See you next Monday.
Then you said policy iteration is faster than the value iteration. I thought the policy is faster than the value.
Yeah, policy.